Welcome to Math, Week 4, Absolute Value Equations and Inequalities. This is Module Math-1 on the Math Tutor Self-Study track, and today's 120-minute lesson closes the 4-week opening unit with a 10-question practice quiz and a cumulative review covering weeks 1 through 3. The single concept this week is distance from zero. The piecewise definition of absolute value drives every problem in this lesson, and the two structural shapes, bounded interval for less than or equal to, two disjoint rays for greater than or equal to, are the same shapes that show up in L1 regularization and mean absolute error in modeling. Phase A, Math Track, Lesson 4. This video is sponsored by Subthesis. Visit subthesis.com to learn more. Absolute value measures distance from zero. An absolute value inequality bounds how far a quantity can be from zero. The two cases, less than or equal to and greater than or equal to, produce structurally different solutions, and a lot of this week is just memorizing which shape each case produces. Here is the plan. State the piecewise definition, name the two shapes, walk each case, work an example, list the common mistakes, then connect to L1 and MAE in machine learning. Quiz, recap, preview. For any real number x, the absolute value is defined piecewise. If x is non-negative, the absolute value of x equals x. The bars do nothing. If x is negative, the absolute value of x equals negative x. The bars flip the sign. The bars strip the sign. They never produce a negative value. This piecewise form is the engine of every absolute value equation and inequality you will solve this week. Whenever you see bars around an expression, you must consider two cases. One where the inside is non-negative and the bars do nothing, and one where the inside is negative and the bars flip the sign. The two cases on the V-graph are the two branches. The corner at the origin is where they meet. Every absolute value inequality reduces to one of two structural shapes, and naming the shape first is the single most important step. Shape 1. The absolute value of an expression is less than or equal to k. Read, the expression is within k units of 0. This is an intersection. The solution is one bounded interval. Shape 2. The absolute value of an expression is greater than or equal to k. Read, the expression is at least k units away from 0. This is an OR, a union. The solution is two unbounded rays. Once you know the shape, the rest is mechanics. Last week's compound inequality moves. Almost every error in this lesson comes from not stopping to identify the shape first. Case 1. The absolute value of an expression is less than or equal to k. This means the expression is within distance k of 0 in either direction. So the expression is at least negative k and at most k. Rewrite it as a compound inequality. Negative k is less than or equal to the expression, which is less than or equal to k. Solve all three sections simultaneously, just like last week's compound and inequalities. Geometrically, the solution is one bounded interval centered on 0 with radius k. If the inside expression is shifted, like the absolute value of x minus 3, the interval is centered on the shift point. Case 2. The absolute value of an expression is greater than or equal to k. This means the expression is at least k units away from 0 in some direction. So either the expression is less than or equal to negative k, or the expression is greater than or equal to k. Rewrite as two separate inequalities joined by OR. The expression is less than or equal to negative k, or the expression is greater than or equal to k. Solve each one independently and report the union. Geometrically, the solution is two disjoint unbounded rays, the complement of the bounded interval from case 1. Do not try to compress these into a single chained inequality. There is no chained form for OR. Worked example. Solve and graph the absolute value of 2x minus 5 less than or equal to 7. Step 1. Recognize the structure. The inequality is less than or equal to, which is case 1, and intersection 1 bounded interval. Step 2. Rewrite as a compound inequality. Negative 7 is less than or equal to 2x minus 5, which is less than or equal to 7. Step 3. Add 5 to all three sections to isolate the variable term. Negative 2 is less than or equal to 2x, which is less than or equal to 12. Step 4. Divide all three sections by 2. Negative 1 is less than or equal to x, which is less than or equal to 6. In interval notation, the closed interval from negative 1 to 6. The number line graph has closed dots on negative 1 and 6, with shading between them. Notice both endpoints are included because the original inequality was weak, preserved through every operation. Second worked example. Solve and graph the absolute value of 3x plus 6 greater than or equal to 9. Step 1. Recognize the structure. The inequality is greater than or equal to, which is case 2, or union 2 unbounded rays. This is the opposite shape from the less than or equal to example we just did. Step 2. Rewrite as two separate inequalities. 3x plus 6 is greater than or equal to 9, or 3x plus 6 is less than or equal to negative 9. Step 3. Solve the left branch. Subtract 6 from both sides. 3x is greater than or equal to 3. Divide by 3. X is greater than or equal to 1. Step 4. Solve the right branch. Subtract 6. 3x is less than or equal to negative 15. Divide by 3. X is less than or equal to negative 5. The solution is x is less than or equal to negative 5, or x is greater than or equal to 1. In interval notation, the closed interval from negative infinity to negative 5. Union, the closed interval from 1 to positive infinity. The number line graph shows two rays pointing outward from closed dots at negative 5 and 1. Notice the gap in the middle. Between negative 5 and 1, no values satisfy the inequality. This is the signature shape of a greater than or equal to absolute value inequality. 9. Here's the side-by-side summary. This is the single most important slide to memorize because the two cases look similar but produce structurally different solutions. On the left, less than or equal to. The key word is and. You rewrite the absolute value as a compound inequality. Negative k is less than or equal to the expression, which is less than or equal to k. The solution is one bounded interval, a segment on the number line with both endpoints included. On the right, greater than or equal to. The key word is or. You rewrite as two separate inequalities. The expression is less than or equal to negative k, or the expression is greater than or equal to k. The solution is two unbounded rays shooting outward in opposite directions. The shapes are complements. If you shade the interval for less than or equal to, and then shade the rays for greater than or equal to using the same k, together they cover the entire number line. One is the inside of the interval, the other is the outside. If you can draw both shapes from memory, you have the entire structural framework for this lesson. 10. Before you split any absolute value equation or inequality into cases, you must isolate the absolute value expression on one side of the equation. If you skip this step and try to split with extra terms still attached, you will get wrong answers. Here is the example. The absolute value of x minus 1 plus 2 equals 6. The wrong move is to drop the bars immediately and write x minus 1 plus 2 equals 6. The right move is to subtract 2 first, giving the absolute value of x minus 1 equals 4. Now the bars are alone, and you can split. X minus 1 equals 4, so x equals 5, or x minus 1 equals negative 4, so x equals negative 3. The rule: always isolate the absolute value term before splitting into cases. This is the forgot to isolate trap, and it is one of the most common errors in this lesson. 11. 3 special cases to check before you start solving. These are situations where you can determine the answer by inspection without splitting into cases. First, the absolute value of an expression equals a negative number. Example, the absolute value of x equals negative 4. Absolute value measures distance from 0, and distance is never negative. There is no real number whose absolute value is negative. The answer is no solution. Stop immediately. Second, the absolute value of an expression is less than or equal to a negative number. Example, the absolute value of x plus 3 is less than or equal to negative 2. If the absolute value can never be negative, it certainly cannot be less than a negative number. Again, no solution. Stop immediately. Third, the absolute value of an expression is greater than or equal to 0, or the absolute value equals 0. The absolute value of anything is always greater than or equal to 0, so the first one is true for all real numbers. The absolute value equals 0 only when the expression inside is exactly 0, giving one solution. These are trivial cases. The rule is, always check the right-hand side before splitting. If it is negative and the inequality demands the absolute value be equal to or smaller than that negative, there is no solution. This saves you from doing work that produces phantom answers. 12. 3 traps to call out before the quiz. 1. Dropping the absolute value bars and only solving the positive case. If you turn the absolute value of 2x minus 5 less than or equal to 7 into 2x minus 5 is less than or equal to 7 and stop, you get x is less than or equal to 6, and you lose the entire lower bound. The bars must split into 2 cases. 2. Forgetting to flip the inequality when multiplying or dividing by a negative. Last week's flip rule still applies inside absolute value problems, especially when isolating the absolute value term first requires a sign flip. 3. Confusing the less than or equal to and greater than or equal to structures. They produce structurally different solution shapes. Less than or equal to is one bounded interval. Greater than or equal to is 2 unbounded rays. Memorize the shapes, diagnose the structure first, then run the mechanics. Absolute value mechanics are the direct mathematical foundation for 2 cornerstone machine learning techniques. L1 regularization, also called lasso. It adds the sum of the absolute value of theta sub j over all weights as a penalty term in the cost function, encouraging weights to shrink to exactly 0. The result is a sparse model. Most features end up with weight 0, leaving you with a small, interpretable subset. The key property: the corner at 0 in the absolute value of w has a discontinuous derivative, and that corner is what lets gradient descent push weights all the way to zero rather than just close. Mean absolute error, MAE, 1 over m times the sum of the absolute value of y sub I minus y hat sub I. Unlike mean squared error, MAE does not square errors, so it is more robust to outliers. The absolute value intuition you build here shapes how you reason about loss functions later. Beyond these two, understanding the bounds of absolute values is also required for defining margin boundaries in support vector machines and confidence intervals in statistical inference. Time to check understanding. 10 questions ahead. Pause after each prompt and try it before I reveal. The quiz targets the trap families this lesson named: the single case trap, the force it through trap, and the structural pattern confusion. Hit all 10 and you have closed the 4-week opening unit clean. Question 1. Solve. The absolute value of x equals 7. Pause. The answer is x equals plus or minus 7. Both 7 and negative 7 have absolute value 7. They are equidistant from 0. Choices A and B individually are the single case trap, where students write only one branch of the case split and lose the other half of the answer. D rules out the existence of solutions, but distance equal to a positive number is always achievable in two directions. Question 2. Solve. The absolute value of x minus 3 equals 5. Pause. The answer is x equals 8 or x equals negative 2. Set the inside equal to plus or minus 5 and solve each case. Case 1. X minus 3 equals 5, so x equals 8. Case 2. X minus 3 equals negative 5, so x equals negative 2. Choices A and B are the single case trap. Choice D, x equals plus or minus 5, is the no shift trap. Students forget to undo the minus 3 inside the bars, and just write the right-hand side as if the absolute value bracketed x alone. Question 3. Solve. The absolute value of x equals negative 4. Pause. The answer is no solution. Absolute value is the distance from 0, and distance can never be negative. There is no real x for which the absolute value of x produces negative 4. Choice C, x equals plus or minus 4, is the force it through trap. Students see the absolute value bars and reflexively write the plus or minus answer without first checking that the right-hand side is non-negative. Always confirm the right-hand side is greater than or equal to 0 before splitting cases. Question 4. Free response. Solve the absolute value of 2x minus 5 less than or equal to 7 and give the interval. Pause. The answer is the closed interval from negative 1 to 6. The inequality is less than or equal to, so case 1, rewrite as the compound negative 7 is less than or equal to 2x minus 5, which is less than or equal to 7. Add 5 to all three sections. Negative 2 is less than or equal to 2x, which is less than or equal to 12. Divide all three by 2. Negative 1 is less than or equal to x, which is less than or equal to 6. In interval notation, that is, the closed interval from negative 1 to 6. Closed brackets because the original inequality was weak. This drills the structural pattern that less than or equal to becomes intersection, one bounded interval. Question 5. Free response. Solve the absolute value of x plus 2 greater than 3 and use interval notation. Pause. The answer is the interval from -infinity to -5, union the interval from 1 to infinity. The inequality is strict greater than, so case 2, union of two rays. Rewrite as x plus 2 is greater than 3, or x plus 2 is less than -3. Solve each. X is greater than 1, or x is less than -5. In interval notation, open parens on infinity and on the strict inequality endpoints, joined by the union symbol. This drills the structural pattern that greater than becomes union, two disjoint rays. Question 6. The equation, the absolute value of 3x equals 12, implies what? Pause. The answer is x equals plus or minus 4. Set 3x equal to plus or minus 12. Then divide both candidates by 3 to get x equals plus or minus 4. Choice D, x equals plus or minus 12, is the trap, where students forget to divide by the coefficient on x, they read the right-hand side and copy it as the answer. Choices A and B are single case traps. Always divide by the coefficient after splitting cases. Question 7. Free response. Solve the absolute value of x minus 1 plus 2 equals 6. Pause. The answer is x equals 5 or x equals -3. Isolate the absolute value first by subtracting 2. The absolute value of x minus 1 equals 4. Then split into cases. X minus 1 equals 4, so x equals 5, and x minus 1 equals -4, so x equals -3. The forgot to isolate trap is the failure mode. Students who skip step 1 try to split with the plus 2 still attached and end up with garbage cases. Always isolate the absolute value term before splitting. Question 8. Which machine learning loss function is built on absolute value? Pause. The answer is C, mean absolute error. MAE is the mean of absolute residuals. 1 over m times the sum of the absolute value of y sub I minus y hat sub I. Because it does not square the error, it is more robust to outliers than mean squared error. MSE squares the residuals. Cross entropy uses logs of probabilities. Hinge loss uses a piecewise max formulation. MAE is the loss that maps directly onto this week's absolute value mechanics. Question 9. Which regularizer corresponds to summing absolute values of weights? Pause. The answer is L1, also called lasso. The L1 penalty is the sum of the absolute value of theta sub j over all weights, and it produces sparse models. Most weights are driven to exactly 0 because of the corner in the absolute value function at 0. L0 counts non-zero weights, combinatorial, not differentiable. L2 sums squares, producing the smooth quadratic ridge penalty without the corner. Frobenius is the L2 norm generalized to matrices. Question 10. The reveal question. Why does L1 regularization produce sparse models while L2 does not? Pause. It is all about the corner. The gradient of the absolute value of W is constant, plus or minus 1, until W hits 0, and at 0, the gradient has a kink, a discontinuity. That kink lets gradient descent push the weight all the way to 0 in finite steps. The gradient of W squared, on the other hand, is 2W. It shrinks proportionally as W approaches 0, so the updates get smaller and smaller. The weight approaches zero asymptotically, but rarely actually reaches it. The sharp corner of the absolute value function is the entire reason L1 yields sparsity and L2 does not. You translated absolute value equations into the positive and negative cases, decoded the structural pattern that less than or equal to produces a single bounded interval and greater than or equal to produces a union of two unbounded rays, and connected absolute value mechanics to L1 regularization and mean absolute error in modeling. The takeaway is that the absolute value of x means distance from zero, and distance is never negative. That single fact diagnoses no solution cases instantly. 3 trap families fell this week: the single case trap, writing only the positive split; the force it through trap, assigning a value to the absolute value of x equals negative k instead of declaring no solution; and the structural pattern confusion, mixing up the interval shape for less than or equal to versus greater than or equal to. The cumulative review reinforced PEMDAS, multi-step isolation, the inequality flip rule, distribution with negatives, and identity versus contradiction diagnosis from weeks 1 through 3. That closes the 4-week opening unit. Next week, you broaden from 1 variable to 2, pairs of linear equations forming a system. You will learn substitution and elimination, the algorithmic precursors to matrix inversion that powers closed-form linear regression and computer graphics. Solutions become points in the plane rather than numbers on a line, and you will classify systems by whether the lines meet at one point, run parallel, or coincide. That wraps up Week 4 and the 4-week opening unit of Math-1. Thanks for studying. If this lesson helped, please like and subscribe. It tells the algorithm to put this in front of more learners. See you next week for Systems of Equations. Sponsored by Subthesis, subthesis.com.